So welcome to this session of the NPTEL learning course on engineering methodology. And today we will be dealing with the pressure transducers. So let us begin our discussion today. So in the previous sections and in the previous lectures, we have dealt in detail with the concept of transducers and the physics behind the transducers and how the mechanical measurements were converted into electrical measurements, and how does a transducer converts a physical variable into electrical signals. We dealt in detail with the temperature measurements, and we saw how does the thermistors, thermocouples, and different other types of temperature transducers work. What are their applications, what are their ranges, and in what different scenarios what different transducers should be used. So today our discussion deals with the measurement of the pressure. Now, to understand the pressure transducers, let us quickly recap what does pressure exactly means. So we all know that in mathematical terms we say pressure is force per unit area. So suppose I have a substrate, and on this if I apply some force, on this if I apply some force and say the cross sectional area of this in two dimension is A, then on per unit basis, how is this force distributed over this entire substrate is the measure of the pressure. Let us go deeper into this and understand what exactly is stress and what exactly is strain, and how are these two different. So say I have a cylindrical pipe of length L, and this has a cross-sectional area of A. Now if a force is applied to this particular point, then we calculate stress is F by A, which is almost similar to the pressure that we defined, or exactly the same, rather than saying it to be similar. Now suppose we apply the force, and the nature of the force varies. Now how does it vary? It can be compressive, that is, it causes compression, or it can be rarefaction, that is elongation. So if the direction of force is like this, so what it will do is it will start to compress this body. On the other hand, if the direction of the force is directed outwards, then it will cause an elongation in the body. So when the nature was compressive, the length was shrinking, while when it was directed outwards, it caused an elongation. So this length L in both the cases was changing. Now if I want to model this strain, so what can I say this strain to be? This is L minus L1, that is the new length, divided by the original length L. So this particularly, strain particularly, is a dimensionless quantity. And what it represents is the deformations that is caused due to the applied stress. So if we see this on a broader picture, what we have is a body on which we are applying the force, and this force is proportional to the pressure, or rather the pressure is proportional to the force. So we should say this force creates a pressure, and that we can also term as the stress, and this stress in turn causes the strain. So our line of command here is, because see, when we are designing a transducer or an instrumentation system, we have seen that we need to model the physical variables into electrical signals. So what happens here, let us see afresh again, that we applied force which created some pressure, and that caused the strain. Now this strain is a very simple term, that it is changing the dimensions of the substrate or the body under study. So what we have boiled down to is that to a corresponding force there will be a corresponding change in the dimensions of the substrate. So if I can model this strain or the change in the dimensions of the substrate, I am very much sure that I will be able to model the force that is being applied or the pressure that is being applied. So if this point is clear, we are very sure that we are going to measure the linear changes caused by the pressure which can be non-linear in itself. The pressure can be of any kind, and we need not worry about how this pressure comes or how this pressure changes. How we have created the flow of this problem as that with the applied pressure, there is a change in the linear properties of the body. The length of the material would change, and if we can measure the change in length of the body, we are pretty much sure that we will be able to convert that change in length into an electrical signal that will correspond to the change in the force. So the next line of command that comes here is that with the force we apply a pressure, and with the pressure there comes a strain, and that strain is, say, change in length. And if we measure this change in length, we create an electrical voltage, and this delta V will give us the direct correspondence with delta F. So the curve that we get finally is the curve between our variable is delta V over time, and this delta V corresponds to delta F. So with the progression of time, the way the voltage changes, we say that in the similar fashion, the forces will also be changing. Now, why are we studying this physics again, and what is the application of these areas? So, if you go to process industry, like the power plants where electricity generation is being done, say a thermal plant or a hydro plant, that does not matter, but in all the processes there is a lot of pressure valves. How? Suppose this is a thermal power plant, and in the thermal power plant we have a turbine that is rotating, and the rotation in the turbine is generated from the temperature of the fuel being burnt. So in the mid of this, what we have to do here is we have to create a mechanical action of rotating this turbine, and rotation is caused by the pressure being exerted on the turbines, and this pressure in turn is generated by the temperature. So we have here a lot of high pressure valves, and every time we need to measure the pressure over here. Any drastic changes in the pressure, say the temperature dips down to a very low value. So all of a sudden, this has to be released to stop the turbine. Otherwise, it will cause a malfunction in the entire process. A similar case is of a blast furnace. Say we are working in a glass industry and the molten glass is flowing in the tubes and it has a very high temperature, and with the flow of the liquid a pressure is created. Now if the flow of the liquid changes due to some of the variables being changed, there is a dip in the pressure, and that dip in the pressure has to be accounted for the dip in the temperature, and again we see these kind of walls. So in process industry, it is very important for us to measure the temperatures and the pressure values at different times and different positions of the entire process. So if this concept is clear that how the force in turns create pressure and that pressure is modeled to an electrical voltage, let us now move on to designing a pressure transducer. Now if we consider this force voltage relationship, we have to design a system in such a way that this forces that are causing the elongation or compression converts into voltages, and those voltages are being measured accurately. So we need to have a twofold approach here. First is a physical device that causes change in length corresponding to change in forces. And then comes an electrical device that can convert the change in length into the change in voltage. So the entire process that we studied, we have broken it down into two parts, wherein for the first part there is a physical device that converts the forces being applied into change in lengths, and then comes the second device, that is an electrical device, which models this change in length into corresponding change in voltages, and then we can easily measure the voltages using normal voltmeters and multimeters. So the devices that we are going to study here are bellows, Bordel tubes, and diaphragms. And the devices that we are going to read here are resistive potentiometric capacitive and piezoelectric. Based on these criteria, whether a resistive method is used or a potentiometric method is used, the class of the transducer is defined. So say we are using a resistive method that we will deal here, we will call this type of transducer as the resistive transducer, and if we are using a capacitive method, we will call our transducer to be a capacitive transducer. Now let us move on and understand the physical properties and rather the physics of these devices which create a change in length due to the change in the forces. So let us open this discussion with the diaphragms. Now if you remember from your early classes where we discussed a few things about the physical properties, I have been using this name. Diaphragms are elastic materials that cause a change in shape when subjected under load. So let us say we have this kind of a substrate and this is a flexible material that has elastic properties. Now what will happen is when we apply force onto this surface, this will cause a deformation and the shape would change like this. So this, if I consider as my baseline, there will be a change in the property of this material. And this simple mechanism is called as the diaphragms. Now this delta D corresponds to the force F. If this F changes to F dash, the delta D will change to delta D dash. Or rather, it will be delta D only, but the change, if it was D, small d, then corresponding to the F dash, it would be D dash. So this is one mechanism with which we can very commonly calculate the application of force on elastic materials, and it causes the change in the dimensions of the material. And this change in the dimension of the material is to be studied by different methods. So with this, we move on to the next type of elastic material that we discussed, and that is called as the Borden tube. The Borden tube again is classified into two types, that is the C-type Borden tube and the spiral Borden tube. And this totally depends on the shape of the section that we are using. So let us suppose we consider this first C type. So this is the normal shape of a C, and one of its end is closed and is hinged to a say a straight line. This will be used as the marker. And now let us say this is the end at which we start applying pressure. So because one of its end is fixed and on the other end we are applying the pressure, the change in the pressure will start to create deformation and the changes in the dimension of this CPU. And corresponding to the dimensions changes, this marker would deflect. So let us say at the base position it was here. After the application of force, the bending occurs or the deformation occurs, and this marker moves from here to here. And we measure this angle theta, and that theta angle is converted into linear displacement, and we are pretty much sure that we have converted this pressure being applied onto this section into delta L. That was our aim. Another type of design that is used for designing the Borden tubes is the spiral. Now, while we design the spiral tubes, let us say we have a design like this. And at this end, we close this tube. and here again we apply a marker, hinge it to this marker, and we apply pressure over here. So if you closely observe this figure, a spiral type is nothing but parallel arrangement of multiple C sections. So what it does is it allows us to apply larger forces and pressure. Why? Because of the number of turns that are being involved in this spiral, we have a capacity to apply more pressure, and with the larger amount of pressure, the opening and closing of this spiral happens. And that opening and closing is read here with the marker. So this again creates a deflection delta B. So the only benefit that we have, concept-wise, C-type elements and spiral elements are the same, but the benefit that we get here is we can measure much larger forces with larger sensitivity. What does this mean? This means that if C-type was capable of judging, say, X pascals, the spiral type can measure Y pascals, wherein Y is much lesser than X. So for very small changes, very small changes in the pressure, we can use this spiral type device. And you can see commonly that in all these devices, whether it was a diaphragm or a C-type or a spiral type Bourdon tube, we have been engaged in converting this pressure into the change in length. So we want a linear change in dimension corresponding to a complex force. Now moving on, the next device that we will see here is bellows. Now again, the function will still be the same, that we have to apply the forces or the pressure, and correspondingly we have to measure the deflections in the tip or the deflection in the length to which the tip is binded. So let us see the structure of the bellows. So this is a typical example of a bellow. What we are doing here is at the top here, or maybe at the bottom, we apply a pressure P. Now once this pressure is applied, this D will start to compress. All these will start facing compression, and this D will now change to D dash, and delta D will correspond to D dash minus D. Now if there is a method by which we can measure this D dash, we are pretty sure that we have modeled this pressure into length, and that length into, again, electrical voltage. So these are three broader classes of the physical devices that we use for converting the pressure into the linear dimensions. So now let us move on to the next section, where in which we want to convert the dimensional changes into electrical signals. So now when we are converting these dimensional changes into electrical signals, we will have to look for the material properties that correspond to changes in the dimensions. And a very well-known property of such type is the resistance of the material. How? If I have a cylindrical cross section like this, which has a cross sectional area of A and length L, I can define the resistance R of this length to be rho L upon A. Where this rho is the material property called as resistivity, which depends on material to material. So I can directly see that R is directly proportional to L, and we have been doing several experiments previously, like diaphragms or bellows or Gordon tubes, in which the pressure was being used to create changes in the length. Now, if we try to find a correlation, we are trying to say that pressure creates a change in length, and the change in length creates a change in resistance. So if I talk in terms of delta movements, I'll say that change in pressure creates change in length, and that creates change in resistance. All I have to do is to design a system such that I can measure this change in resistance. And if I can change this, measure this change in resistance, I can go in the reverse fashion and say that this corresponds to change in length L, and this corresponds to change in the pressure P. So the crux of my design of a pressure transducer is to find a property that corresponds to the change in the linear dimensions. One such property we have seen is the resistance. So let us now study in detail these resistive pressure transducers. So we all know the concept of the potentiometers, and let us begin with the simple method of the potentiometer, wherein I work on a variable resistor with a joystick or a jockey. So this basically is a fixed resistance, and I have a jockey that can move onto this or slide onto this part of the resistance. Now when it slides, it changes the length that it covers, and with the change in length L, the resistance increases with the same formula of R is equals to rho L upon A. Lower the length, lower the resistance, higher the length, higher the resistance. Now if I apply a battery over here, there is a current flow I, and I can measure this current flow I, and I can calculate this resistance R. Or if I don't want to do this, I can just simply connect a galvanometer across this, and this galvanometer deflection will give me the value of the resistance over here. So if I want to design a transducer in such a fashion, what I can do is, let us say we did it with the diaphragm. So let us say this was my diaphragm, and I applied a pressure P onto this, which caused a depression like this. Delta T. Now, if I have a variable resistor or a potentiometer like this connected to the galvanometer here, and there is a jockey. This jockey is now connected physically to this diaphragm. On the base position, when it is here, it will show some value R, and as soon as the pressure is being applied, it bends down, and when it bends down, this moves further. When it bends down more, this moves even farther. And when it comes to this position, it reaches a peak value and it gives you the resistance R. So here is a clear demarcation of the two systems that we were talking. One is the physical system that converts pressure to delta D, and then comes the electrical system which converts delta D into V, and we find a relation finally between P and V. So with changes in voltage, we correspond the changes in pressure. And for similar sections, like of a C tube, if we apply pressure here and it is fixed, and this fixed movement is connected to a potentiometer, the more pressure you apply, the more it bends. The more it bends, the farther it moves. The more it bends, the farther it moves. The more it bends, the farther it moves. And we get different resistances for different pressure. So the first type of resistive transducer that we studied was a potentiometric transducer. A very commonly used type of resistive transducer is called the strain gauge. This is very important, and in almost all the applications we use a strain gauge because of the sensitivity of this device. It gives you a very high range of sensitivity. And what is a strain gauge? A strain gauge is nothing but a full bridge or Wheatstone bridge that you are very well aware of. So if I have a full Wheatstone bridge like this, R1, R2, R3, and between these two terminals, if I apply my galvanometer, I can see the deflections. And here we apply our strain gauge. And strain gauge is what? It is nothing but on a non-metallic piece of substrate, we create metallic strips. Now again, when pressure is applied onto this strip, the dimensions would change, and with the change in the dimensions, the resistances would change. And what we are eventually doing is, we are connecting this with this Wheatstone bridge. So this section will create delta R, and this delta R will cause a deflection over here in the galvanometer. We will deal with a few numericals on this in the next class also to better understand the concept of how this delta R is creating the changes over here. But should be well versed with the concepts of KCL and KVL to solve the problems here. Next, after having studied the resistive transducers, let us go on to look how do the capacitive transducers work. So for this, let us revise our concept of a parallel plate capacitor. So let us say this is a metallic plate on which we have positive charge, and this is another plate on which we have negative charge. So we have a flow of electric field over here, and if this material is filled with the dielectric, with the dielectric constant of say epsilon naught. So we can say that this particular setup forms a capacitor whose value is epsilon naught A upon B. Now again, we see that this capacitance C is interdependent on the plate area A and the distance B. So we can say that C is inversely proportional to B. Now let us not focus here what are the charges Q and the voltages, because eventually what we have to find is a relation of length with the value. So while in the resistance we said that resistance were directly proportional to the length L, what here we are saying is that if the distance D between the two plates of a parallel plate capacitors are D, then the capacitance is inversely proportional to this distance D. So eventually this would mean is if we reduce this distance D, the capacitance will go on to increase, and if we increase this distance D, the capacitance will be reducing. So eventually, if I design a mechanism by which if I apply a force F onto the parallel plates and these parallel plates start coming closer to each other and this D reduces, the capacitance will increase. But if the force are causing an elongation, the capacitance would reduce. So let us see such a system wherein we can directly place our force methods to identify these capacitances. So let us say I have a box like this, which is totally sealed, and here I have a plate of a capacitor and this end is fixed. This cannot move, and this is the first plate of the capacitor which is subjected to forces, and this is made up of elastic materials just like diaphragms, and all over here filled is the dielectric. Now if force F is applied, the diaphragm will start to bend, and we will see that this distance between the two plates will eventually start to reduce to d dash, and we have seen that C is epsilon naught A upon D. That is, with reducing D, the capacitance will go on to increase. So, when we are applying a force in this fashion, the capacitance will increase. So, if this is F compressive, the capacitance will, with the increase in compressive force, the capacitance will increase. And with the increase in capacitance, we know that the charge on the capacitor is Q is equals to CV, so that C is Q by V. So once the C is increasing, this voltage will start to dip down. So with the compressive forces, the voltage would be reducing. Whereas on the other hand, if this is not compressive but expansion causing force, what will happen is this distance will increase, and with increase in this distance, the capacitance will reduce. And with this reduce in capacitance, the voltage will increase. So this is the concept of a capacitive type of force transducer. Another type of force transducer that we should see here is a piezoelectric crystal. Now in multiple discussions we have seen what are piezoelectric crystals. Let us see again how does a piezoelectric crystal converts the pressure into voltages. And for this, let us see a setup wherein we are applying pressure over here. And here we have a piezoelectric crystal. So we have seen for material like quartz, when external pressure is applied, without any supply or anything changed, it creates a potential difference or basically voltage. Now, if this is the case, if we apply a galvanometer over here, this will start showing us deflections. Why? Because this pressure when applied to this plate will eventually compress this piezoelectric crystal, and with the properties it will start causing generation of potential difference E over here. So what again we have done is this pressure causes in the changes of the dimension d, and these changes in the dimension d eventually generated E, and that E corresponds to P back. So again, with the pressure we have a voltage relation, and all these voltages can easily be measured by multimeters. So this was in just a broader discussion about the pressure transducers. What are the type of pressure transducers? What are the different physical aspects to designing pressure transducers, and different other factors that we should be considering while designing the pressure transducers. Now, before we move on to the next section, we shall look for a few numericals based on the strain gauges in the next class. And also we will be looking for different types of non-contact type of temperature sensors that we skipped in the last class. We have seen contact type temperature sensors, but for very high temperature corresponding to say 800 degrees Celsius or 1000 degrees Celsius, where materialistic contact is not feasible, we should look for non-contact type measurements. Now let us move on and study the components of a mechatronic system. So a mechatronic system, as you can see from the word, derives from two root words. One is mechanical and the other is electronics. So eventually we are designing control mechanical arrangements with electronic systems. And this is one big aspect wherein our transducers are being extensively used in almost all the scenarios. So let us say I have to create a valve control. Now let us say I have a reservoir tank, and this reservoir tank is being supplied with water for an entire village, and it has a capacity of 50,000 liters. Now with the flow being variable, we cannot count the time required to fill this 50k liters of water. In that case, we have to design a system wherein when this tank is completely filled, I should cut off the supply from the baseline. So what are the different aspects to this? First is a system to measure the tank being filled. Second is a system that interprets the answer by system 1. And the third is a system to close or open the valve as directed by system 2. So when we see this, we can draw the block diagram of this system as a master control unit that can interpret all the decisions, a transducer or a sensor that can measure the level of the tank, and an actuator that can open or close the valve. So this is a basic open loop system. So now if I move from being very figurative to rather specific, we would need a embedded controller or a control system which is, let's say, our computer, an algorithm that processes all the variables, a level sensor which can be infrared sensor or ultrasonic sensor, and then a DC motor to open or close the valve. This is the basic mechatronic system that applies almost everywhere. Similarly, for controlling the process industry, we have a device which is called as SCADA, which stands for supervisory control and data acquisition. So what it does is, on the plant, it has several units to capture sensor data, and by the help of telemetry, the sensor data is transferred to the master station, where at the master station different controls are being generated and feedbacks given back to the plant. So with this, we will close our session today here, and in the next class we will start with the few numericals on strain gauges. We will look for non-contact type of temperature sensors, and then we will move ahead with our next further topics of discussion. If you have some queries, you can post it to the mailbox that was told to you earlier. Thank you.